Today we are going to discuss about a different type of controllers in a control system. So first of all, there are different types of controllers like proportional controller, derivative controller, integral controller, and then we can use according to our requirement. Like either we can use the proportional integral controller, proportional derivative controller, and proportional integral derivative controllers. So we will discuss about one by one now. First, we are going to discuss about a proportional controller. So this particular controller is a simple form of controller, and we will use this proportional controller to reduce the error between the process output as well as the set point. Here, as I discussed in the previous lecture, set point means we can call it as an input also, input which we will give to the system. So here we will use the proportional controller to reduce the error between the set point and the output which we will get from the system. And then in this particular proportional controller we have only one adjustable parameter to get the desired output. So what is that adjustable parameter here? In proportional controller we can adjust the gain of the system. We can adjust the gain of the system or process to achieve our desired output. Okay, and then here whatever the output signal which is produced in this particular controller, when we use this particular controller, whatever the output signals which we will get from the system, those will be in proportional with the error value which is produced in the process. So as the name suggests, proportional controller, here the output signal which comes from the system or the process is proportional to the error produced in the process. So for this process we can write down the equation like this. This is the proportional controller equation. Capital P equal to Kc into E plus small p upon s, Ps. What is P here? P is the output value. Of course, as I told you, we are checking out the output signal. What is the desired output we are going to get? So P, that is output signal, capital P is the output signal, and Kc is the proportional gain or sensitivity, and here the E is error value. How we can find out the error value? That I have explained in the previous lecture. That is error value equal to set point minus measured value, and Ps is the constant value. Ps here it is a constant value that we will call it as steady state output from the controller. And now if you write down this output value, we can write down in a simplest way, like capital P equal to, this is the capital P and this is the small p. So capital P equal to, that is the output signal equal to the proportional value minus the steady state value. Okay, and then this equation you can write down by applying the transfer function. What you will get? Pt equal to Kc epsilon t. So now if we apply the transfer function, then we will get the equation as Kc equal to, that means the what is the transfer function here? When we are applying the transfer function, you can call it as, it is a relation between the output signal and the input signal. So this is the our input signal and this is the error we are getting here. So what you will get it? You will get the transfer function Ps by Es equal to Kc. Kc is the proportional gain. And now actually when first we will get this diagram. Okay, so this is the behavior of the proportional controller. So the proportional controller, actually what happens, it will be a steady state line, a straight line, okay, and it will behave like a ideal. It is an ideal conditions. It is an ideal condition graph of the proportional controller. You will get a slope here and you will find out the bias value, or we can get it as a constant value, that we will call it as steady state value. But this is for the ideal case, but that will not happen in the actual. So in actual what happens, you can see the diagram here, this diagram. So actually when we start the process, initially it will be in a steady line, and due to the changes, due to the inputs we will give to the system, then there will be a rise in the curve, and then after that, once it reaches the steady state, again it will come back to the saturation. Okay, saturation. So initially it will be in a saturation point due to the changes in the input at the set point, the increase in the output you will get, and after that it will be in the steady state. Steady state. So where that means in real it will have a P minimum value as well as it has a P maximum value, and you will get again you will get a that is a bias value you will get. Okay, this is for the ideal case and this is for the real case. Okay, I hope you understood. Now we are going to see the second type of controller, that is proportional integral controller. So here what we are doing is we are adding an extra element to the proportional controller, that is an integral action to the proportional controller. So why will we add this integral controller? Because as we know, as we discussed in previous one, the proportional controller we will use to remove the error in the process. But this particular proportional controller cannot remove 100% of error. So there will be some leftover error. So that we will call it a residual error. So to remove that residual error, we will use the integral action. We will add the integral action to the proportional controller. And when we use this proportional integral controller, then we will use the error. We will get the error value is 0. Ultimately, the error value will get as a 0. And in this proportional controller, we have two adjustable parameters. So by using these two parameters, by changing these two parameters, we can achieve the desired output. What are those parameters? First one is that you can change the gain of the process, or you can change the integral time. By changing any of these values, you can achieve the desired output. So now, if you see the equation of the PI controller, P equal to Kc E plus Kc by tau I, integral of 0 to t E into dt plus Ps. If you observe this equation properly, then there is a one extra term is added to the proportional controller. If you remember what we discussed in proportional controller, the proportional controller action is P equal to Kc E plus Ps. To that we are adding the integral term. So here, if you apply derivative to this equation, then you will get the equation this one. Pt equal to Kc plus Kc by tau I into t plus Ps. So now if we find out the transfer function, that means the relationship between the input and the output signal, then you will get the transfer function of PI controller is Kc of 1 plus 1 by tau I into S. So now we will let us see the diagrammatic representation of proportional integral controller output. Okay. As you can see here, we are drawing a graph between t and the error values. Okay. So we are breaking down. We are taking the overall output from the system. So first of all, we look into the proportional action. So that is removing the error from 0 to 1. And after that, we are breaking down the graph in between the 1 and Ps value. And here, from the Ps, we have a error. So that error we will find it out. This is the constant Kc value, that is proportional gain, and we will find out the Ti value from the slope. Okay, that we will find it out. Fine. So now we will see the third type of controller. Okay, that is proportional derivative controller. So that we will see now. Okay, we will add a derivative term to the proportional controller, and then we will find out the output of that particular system. Right. Now the third type of controller is proportional derivative controller. as we added integral term to the proportional controller, here we are adding the proportional term, we are adding the derivative term to the proportional controller. Why we have to add the derivative controller? The integral control we have added to remove the 100% of error in the process. But the derivative term we will use when there is a rapid change in the error. When there is a rapid change in the error. In such cases, we will use the derivative controller to remove the 100% of error. Okay? And that means when the output is oscillating rapidly, in such case, we will use the derivative controller to remove the 100% of error. Fine? And if you write the equation of derivative controller, again you can observe clearly we are adding an extra term to the proportional controller, and that is the derivative term. Okay, so that is P equal to Kc plus E. Here the Kc is the proportional gain and E is the error, plus Kc tau d, and the new term here, that is tau d, that is derivative time, and then dE by dt plus Ps, that is a constant value. Okay, and now if we apply the transfer function to this particular equation, we will get the transfer function equation. How we can find out the transfer function equation? By applying the Laplace to the equation. When we apply the Laplace to the equation, then we will get the transfer function as Kc into 1 plus tau d into S. And if you see the action of proportional derivative controller, then the graph looks like this. Here what we are doing, already we have the error value, we are drawing graph between t and the error value, and already we are getting an error value that we have already seen in the proportional derivative or proportional controller, and to that we are adding the derivative controller that finds out the error which is present, the rapid change or the oscillation in the output, whatever the error which is produced, that will be find out by the derivative controller. Okay, here up to here it is only the proportional controller, up to here that is only proportional controller. From here to here, that shows the action of derivative controller which is present in the PID controller. Okay, so now we are going to see the fourth type of controller, that is proportional integral derivative controller. So you may ask me the question like why we have to use the PID controller? Because we already see the proportional integral controller where we have removed the error as well as the residual error, and when we use the derivative controller, we have removed the oscillations, okay, the rapid change or oscillations in the system. And why we have to use the combination of P and T controller? Actually, this particular controller is a most stable controller, and where we will get a desired output, a proper desired output. Okay, there we will remove or minimize the oscillations as well as the sensitivity of the process, and we can increase the stability of the process. Okay, so that is what I have written down here. When we use the derivative controller, of course we can find it out. When the process is rapid, we can remove the error from the process. But where we cannot find it out, how the magnitude of the error or how long the error is taking place, that we cannot find it out. So to avoid that, we can use the PID controller. Okay, and when we use the, as I told you, when we use this PID controller, we can minimize the oscillations and we can minimize the sensitivity of the process, and we can increase the stability of the process. So now, if you write down the equation for PID controller, so it looks like this. Simply you can say, first the proportional controller terminology is KCE plus PC. This is the, I am writing down the one number. So this is the proportional control, right? PID, proportional control. And then I have added the term I. This is the integral action of the controller. And finally, this term is the derivative action of the controller. So P, I, and D. So the combination of proportional, integral, derivative controller equation is looks like this. And now, if you want to find out the transfer function, apply the Laplace transform to this equation, then you will find out the transfer function of PID controller as PS by ES equal to KC into 1 plus tau DES, the derivative controller action, and 1 by tau IS, that is the integral controller action. Okay, so now if we see the whole process, PID controller process, in a graphical representation. So one by one I will explain the first line, that is no action taken, controller action. This line represents the controller action. The first one is the no action. That means that is removing the error, but it is taking a longer time to reach the steady state. It takes a longer time to reach the steady state when the offset value is very high. Okay. When we use the second one, the proportional action, if there is no controller, then it takes a longer time to reach the steady state, the process to reach the steady state, and the offset value is very high. But if you are adding a proportional controller to the system, then what happens? There will be oscillation in the system, but it takes a longer time as compared to less time. When we don't use the controller and proportional controller, it takes a lesser time as compared to the no controller case, but the offset value is little bit high, but there is a oscillation in the output value. And the third one is the proportional integral. When we are adding the integral controller to this proportional action, then it reaches to the steady state very quickly, and the offset value minimizes, and the offset value is very less, but it will not reach the steady state completely. But if when we use the proportional integral and derivative controller, we can observe the line below. Start from here, and in a quicker time it reaches to the steady state. In a quicker time it reaches to the steady state, and the offset value is here. The offset value is 0. Okay, so when we use the proportional integral derivative controller, we can minimize the sensitivity of the process, and we can increase the stability of the process. Okay, I hope you are clear with all the type of controllers, and in the most of the industrial cases people use PID controller and PID controller. Okay, because it removes the oscillations. When the process is in oscillation mode, there are a lot of oscillations in the output. Then it removes that oscillation and it brings to the steady state. And PID controller, it decreases the sensitivity as well as it increases the stability. So mostly in industries, people choose these two type of controllers. I hope the concepts are clear, and in the next video we will see the experimental session of a temperature control breaker.